A silent darkness will eventually consume the cosmos. The stars we see tonight are not permanent fixtures, and the universe's own expansion is pulling them away from us forever. Carl Sagan once said that the cosmos is within us, that we are made of star stuff. This profound connection makes the fate of those stars a deeply personal matter. Exploring the future when galaxies drift beyond the reach of light is not just about astronomy. It is about understanding the ultimate boundaries of reality itself. By the end of this, you will see our place in the cosmos with a startling new clarity. What strange forces are actively rewriting the final chapters of the universe, and what could possibly remain after the last light goes out? How does it feel to know we are living in a uniquely bright and fleeting moment of cosmic history? That loaf of raisin bread slowly rising in the cosmic oven gives us a powerful image. As the dough expands, every raisin moves away from every other raisin. No single point is the center, yet the entire system is growing. This is the reality of our universe, where space itself is stretching, carrying galaxies along for the ride. For decades, cosmologists assumed this expansion was slowing down, that the mutual gravitational pull of all the matter in the cosmos would eventually put the brakes on this grand flight. Then, in the late 1990s, two independent teams made a shocking discovery. By observing incredibly distant stellar explosions called Type 1, a supernova, they found that the universe's expansion is not slowing at all. It is speeding up. This revelation was so profound it earned the Nobel Prize in Physics in 2011. Something was overpowering gravity's relentless tug. That something is dark energy. Think of dark energy not as a substance, but as a property of empty space itself, a kind of anti-gravity woven into the very fabric of the cosmos. Unlike matter or radiation, whose density drops as the universe expands, dark energy maintains a constant density. As the universe grows larger, there is more and more space, which means the total amount of this repulsive energy increases. This leads to a runaway effect where the expansion rate doesn't just remain steady, it actively accelerates. The simplest explanation for this is the cosmological constant, an idea Albert Einstein introduced and then later called his biggest blunder. He initially added it to his equations to keep the universe static, but when we discovered the universe was actually expanding, he discarded the idea. Now it has made a triumphant return as the leading candidate for dark energy, representing a steady, unchangeable energy inherent to the vacuum of space. The implications of this are staggering. Dark energy is the dominant force in our universe's budget, making up about 68% of all the energy in the cosmos. It is the engine that will dictate the universe's ultimate fate. This force is so potent that it will eventually overcome the local gravitational bonds that hold galaxy clusters together. But is it truly a constant, an unchanging rule of physics, or could its strength vary over eons? This remains one of the greatest open questions in science. The answer determines whether we face a future of gradual isolation or something even more extreme. This mysterious pressure, baked into the void, is the primary reason why one day the light from every other galaxy will simply fade away, leaving our own island of stars adrift in an ocean of endless black. That astronaut forever separated from their ship gives us a hauntingly personal image for a cosmic-scale event. Galaxies are not simply flying away through space like rockets. Instead, the space between us and them is continuously stretching, creating an ever-widening gulf. this stretching creates a fundamental limit called the cosmological horizon. Think of it as the ultimate point of no return, the maximum distance from which a beam of light, traveling since the beginning of the universe, could ever hope to reach us. Everything within that horizon makes up our observable universe, the grand stage of everything we will ever know. Yet the entire universe, the whole cosmic tapestry, is likely infinitely larger, with vast realms that are forever beyond our view. The engine driving this separation is the expansion rate, governed by dark energy. A fundamental rule known as the Hubble law tells us that the farther away a galaxy is, the faster it appears to be receding from us. At a certain immense distance, this recession velocity mathematically equals the speed of light. Go any farther, and the galaxy is effectively moving away faster than light can travel towards us. This does not break Einstein's rule that nothing can move through space faster than light, because the galaxy itself is relatively stationary. It is the space in between that is stretching, carrying the galaxy away at these phenomenal speeds. So, what does this look like from our perspective? Galaxies will not suddenly vanish from our telescopes in a flash. Their departure is a far more gradual and eerie process. As a galaxy recedes, its light waves are stretched by the expanding space they travel through. This stretching shifts the light towards the red end of the spectrum, a phenomenon called redshift. The farther and faster a galaxy moves away, the more extreme this redshift becomes. Over eons, the brilliant blue light of young stars will shift to red, then to invisible infrared, and then to even longer wavelengths. The galaxy will not explode, it will simply fade, its light stretched so thin that it carries no detectable energy, dissolving like a whisper into the silent background hum of the cosmos. This is how our universe will visually shrink, the great cosmic light show slowly dimming until only our local neighborhood of galaxies remains visible. This inevitable fading forces us to ask, just how much time do we have before the final curtain falls on the universe as we know it? Our entire recorded history is a single heartbeat in the lifetime of the cosmos. We measure our civilizations in thousands of years, but the universe operates on a timescale of billions and trillions. To understand our future, we must stretch our minds across these almost incomprehensible spans. The journey into deep time begins with the Stelliferous Era, the age of stars we live in right now. This is the bright, bustling period dominated by shining galaxies and ongoing star birth. But this will not last forever. In roughly 100 billion years from now, the expansion of space, driven by dark energy, will have carried every single galaxy outside our immediate neighborhood beyond the cosmological horizon. Their light will be so stretched and diminished that it becomes fundamentally undetectable, leaving our own galaxy and its closest companions utterly alone in an empty void. This isolated collection is known as the local group. Think of it as our final cosmic family, a small cluster of galaxies bound together by their mutual gravity, forever resisting the pull of the expanding universe. This group includes our Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and several dozen smaller dwarf galaxies. While the rest of the universe recedes into nothingness, the members of the local group are on a collision course. Over the next several billion years, the Milky Way and Andromeda will dance a gravitational tango, eventually merging to form a single, larger galaxy, often called Milkomeda. This new island universe will be the final stage for all the stars that remain close to us. After the last star has formed and the Stelliferous Era ends, the cosmos will enter the Degenerate Era. This period, spanning from about 100 trillion to 10 to the 38 years in the future, is named for the stellar remnants that will dominate it. Brown dwarfs, white dwarfs, neutron stars, and black holes will be the primary inhabitants. The galaxy will grow dark, illuminated only by the faint, cooling embers of dead stars and the occasional flash of a stellar collision. Astronomers Fred Adams and Greg Laughlin have mapped out these distant eras in stunning detail, revealing a universe that is far from static even after the lights go out. It is a slow, cold, but still evolving place. The final chapter is the Dark Era. This is when even the black holes themselves evaporate away through a process known as Hawking radiation, leaving behind a dilute sea of fundamental particles and energy. The temperature of the entire universe will approach absolute zero. To say that 100 billion years is a long time is a profound understatement, yet it represents only about 1% of the total lifespan of the smallest, dimmest red dwarf stars. Our entire species, from its first ancestors to its last descendants, will be a flicker in the first moments of the cosmic dawn. This vast timeline does not make our story insignificant. Instead, it highlights the incredible fortune of our existence in this brief, brilliant window where the universe is alive with light, and we are here to see it. As we contemplate this future of a single, isolated galaxy, a new question demands our attention. What will become of the stars, planets, and potential for life within this final, solitary island in the void? A star's life is a constant battle against its own gravity. Our own sun, a vast sphere of incandescent plasma, shines because the immense pressure at its core forces hydrogen atoms to fuse into helium, releasing the energy that lights our days. This process has continued steadily for nearly 5 billion years and will carry on for another 5 billion, but this nuclear furnace cannot burn forever. When a star like the Sun finally exhausts its hydrogen fuel, its outer layers will drift away in a beautiful, glowing shell of gas called a planetary nebula. All that remains is the star's hot, dense core, now exposed as a white dwarf. This Earth-sized ember of carbon and oxygen will initially shine with intense heat, but with no new energy source, it is destined to cool over trillions of years. It will fade from white to yellow to red, and finally to an invisible, cold black dwarf, a dark, crystallized sphere drifting silently through the void. This is the peaceful end awaiting the vast majority of stars. More massive stars meet far more violent ends. When a star many times heavier than the Sun runs out of fuel, its core collapses in a cataclysmic explosion known as a supernova. For a few glorious weeks, this single star can outshine its entire galaxy. What it leaves behind is even more extreme. The core can be crushed into a city-sized ball of neutrons so dense that a single teaspoon of its material would weigh billions of tons. These neutron stars are born spinning furiously, often beaming radiation like a cosmic lighthouse. The very largest stars collapse beyond even that point, their gravity so overwhelming that not even light can escape, forming a black hole. Yet even these dramatic remnants are not permanent. Over timescales that dwarf the current age of the universe, even the protons and neutrons that constitute all matter may themselves be unstable. The hypothetical process of proton decay suggests that over an almost unimaginable 10 to the 34 years, the very building blocks of atoms could simply fall apart, transforming into energy and lighter particles. If this is true, then even the enduring white dwarfs and neutron stars would slowly evaporate, their substance dissolving into a faint mist of radiation. The galaxy, once a brilliant pinwheel of light, would become a graveyard of dark, dissolving relics. This gradual end of starlight is inevitable because galaxies are finite reservoirs of creation. The beautiful nebulae where new stars are born are made from the recycled material of dead ones. Each generation of stars locks away a portion of this gas, either by fusing it into heavier elements or trapping it in stellar remnants. Eventually, the galaxy will simply run out of the raw material needed to ignite new suns. The era of star formation will draw to a close, and the last generation of stars will flicker out, one by one. This cosmic dimming within our isolated galaxy sets the stage for its final, transformative act, a slow-motion dance of gravity that will reshape our celestial home forever. From a future Earth, the night sky would tell a story of breathtaking change. The faint, smudged patch of light we know as the Andromeda Galaxy would no longer be a distant cousin. It would swell month by month, year by year, until it dominated the heavens, a second, brilliant wheel of stars looming beside our own Milky Way. This is not science fiction, but an inescapable future written in the motions of gravity. Our galaxy and Andromeda are locked in a mutual pull, a cosmic dance that will culminate in a merger approximately 4.5 billion years from now. The evidence for this comes from precise measurements of the light from Andromeda. While almost every other galaxy shows a redshift, indicating it is moving away from us, Andromeda displays a blue shift. Its light is compressed, a clear sign it is hurtling towards us at about 250,000 miles per hour. The outcome of this collision is not destruction, but creation. You must forget the idea of stars smashing into each other like cars in a cosmic freeway. The distances between stars are so vast that a direct collision is almost unthinkably rare. Instead, the two great spiral structures will begin a slow, gravitational pas-de-deux, passing through each other, their shapes distorted by immense tidal forces. They will swing apart, then fall back together again, their stars and dark matter weaving a new, tangled pattern over hundreds of millions of years. The final product will be a single, large, elliptical galaxy, often nicknamed Milkomda. For any potential observers within this new galaxy, the night sky would be utterly transformed. The familiar band of the Milky Way would be gone, replaced by a dazzling, spherical swarm of stars. The gravitational chaos would fling some stars out into the eternal darkness of intergalactic space, exiled forever. But it would also compress vast clouds of gas and dust, triggering a brilliant fireworks display of new star formation. The sky would blaze with the light of newborn star clusters and the glowing pink curtains of colossal nebulae. This cosmic renaissance, however, will be the last great burst of activity. After this colossal union, the local group will be a single, consolidated island, with no other large galaxies to consume, and with the ever-accelerating expansion of space having carried all other galactic lights beyond the horizon, the era of galactic interaction will be over. The stage will be set for the long, slow fading of the final stars within this last, lonely galaxy. This final supergalaxy will be the ultimate product of our cosmic neighborhood, a colossal city of stars forged from the complete merger of the local group. The initial union of the Milky Way and Andromeda is just the beginning of a consolidation process that will play out over tens of billions of years. Gravity's patient pull will not be denied. Even after Milkomda forms, the dozens of smaller dwarf galaxies that orbit our local family, including the Triangulum Galaxy, will not escape. Each of these satellite systems is caught in a slow, cosmic dance of decay. Their orbits are not perfect circles, but rather spiraling paths that gradually tighten. This happens through a process called dynamical friction. As a smaller galaxy moves through the halo of dark matter and stars surrounding the larger galaxy, its gravity tugs on these background objects, creating a slight wake or density wave behind it. This wake, in turn, exerts a gravitational drag on the smaller galaxy, steadily sapping its orbital energy. It is like wading through a thick syrup of invisible matter, a resistance that ensures every satellite will eventually spiral inward and be consumed. The supergalaxy grows not just from one major collision, but from a relentless diet of smaller ones. The final structure will likely be a vast elliptical galaxy. Unlike the beautiful, flat spiral arms of the Milky Way, an elliptical galaxy is a three-dimensional swarm, a blobby sphere or football-shaped collection of stars. It will have no distinct features, no bright blue arms of young stars. Its appearance will be uniform, a testament to the violent relaxation and mixing that occurs during so many mergers. All the turbulent, chaotic motions from the collisions will have smoothed out into a steady, random orbit for every star. By this distant era, the galaxy will have long since exhausted its gas reserves. The brilliant bursts of star formation triggered by the initial mergers will have used up the last clouds of raw material. With no gas left to collapse into new suns, the stellar population will consist entirely of aging stars. The galaxy's overall color will shift to a deep, dull red, dominated by the long-lived, low-mass red dwarfs and the cooling embers of stellar corpses. At the heart of this supergalaxy, a dramatic finale will unfold. The supermassive black holes from the cores of all the merged galaxies will have also spiraled into the center. Dragged by the same dynamical friction that consumed their host galaxies, these gravitational monsters will sink to the very core of the new entity. There, they will engage in a final, terrifying dance, orbiting each other in a space that is, by then, packed with the combined mass of dozens of former galactic hearts. As they circle, they will radiate their energy away in the form of gravitational waves, ripples in the fabric of space-time itself. This loss of energy tightens their orbit further, until they finally merge in a cataclysmic event that shakes the cosmos, sending a powerful pulse of gravitational waves out into the void. This supergalaxy will stand alone, a single, immense island in an ocean of nothingness. Its stars will carry the scrambled history of their diverse origins. A star born in the ancient Milky Way could find itself orbiting next to one from Andromeda or a captured dwarf galaxy. Their motions a permanent record of the violent construction project that built their final home. And as this last great structure settles into its final form, we must look beyond its borders to the space that was once filled with the light of countless other islands. This lone supergalaxy will drift in an unimaginable void. Our universe today resembles a brilliant cosmic web, a vast structure where galaxies cluster along glowing filaments like cities connected by highways. Between these threads lie the cosmic voids, immense deserts of near-nothingness that stretch for hundreds of millions of light-years. For now, gravity's bridge connects these great structures, forming superclusters like our own Virgo supercluster, a sprawling metropolis of galaxy groups. But this connectivity is temporary. Dark energy's relentless push is overwhelming the large-scale architecture of the cosmos. The space between these superclusters is not static. It is stretching at an ever-increasing rate, and the gravitational bonds that once held these immense structures in a loose alliance are too weak to resist. They will be pulled apart, while our local group is a tightly knit family bound forever by gravity. The Virgo supercluster is a temporary neighborhood destined for a quiet dissolution. We can already observe this grand exodus in motion. Astronomers use a phenomenon called the kinematic Sunyaev-Zeldovich effect to track the motion of enormous galaxy clusters. They observe how the faint afterglow of the Big Bang, the cosmic microwave background, is subtly shifted as it passes through the hot gas of these clusters. This provides a measurement of how these colossal structures are moving, and the data confirms they are receding from one another, caught in the flow of the expanding universe. The future, therefore, is one of increasing fragmentation. Each gravitationally bound cluster of galaxies will become an island universe, completely isolated from all others. The space between them will be expanding faster than light can cross it. A signal sent from our supergalaxy would simply never arrive at another, its photons stretched into uselessness long before they completed a fraction of the journey. We are left to contemplate the fate of everything within our own island. What becomes of matter and energy when they are locked inside the final, solitary ship, sailing on a sea of eternal expansion? The final supergalaxy is no longer a cradle of creation, but a stellar graveyard. Its once vibrant spiral arms have dissolved into a formless swarm of ancient, fading stars, a city whose last factories have long since shut down. This is the onset of the Degenerate Era, a period beginning around 100 trillion years from now, where the universe is no longer dominated by shining suns, but by their cold, dense corpses. The primary mass of the galaxy now exists as degenerate matter, a term physicists use for the final, crushed state of stellar material, packed so tightly that the rules of quantum mechanics are all that prevent it from collapsing further. The cast of characters is a ghostly one. White dwarfs, the Earth-sized cores of stars like our Sun, slowly cool from searing white to pitch black. Neutron stars, the ultra-dense cinders of supernova explosions, spin down in the silence. And everywhere there are the failed stars known as brown dwarfs, objects too small to ever ignite sustained hydrogen fusion, glowing faintly with the residual heat of their formation. The galaxy has run out of the most crucial resource of all, the free-floating clouds of hydrogen gas that are the raw material for new stars. This gas has either been entirely consumed in earlier epochs of star formation, or it has been blown out into the eternal void by the final, violent deaths of the largest stars. Without this gas, the great cycle of stellar birth and death grinds to a permanent halt. Yet, even in this era of darkness, the galaxy is not completely static. Extremely rare events still punctuate the eons. In the densely packed core of the supergalaxy, the slow dance of gravity can still bring two ancient stars close enough to collide. When two old, cold stars smash together, they can merge their remaining hydrogen fuel, briefly igniting into a new hot star known as a blue straggler. For a short time, a brilliant blue point of light will flare in the darkness, a final, fleeting echo of the galaxy's glorious past. Elsewhere, brown dwarfs may experience faint, sporadic flickers as they manage to fuse deuterium, a heavy form of hydrogen, but these are mere sputters compared to the roaring furnaces of true stars. The most dramatic events come from binary systems, pairs of white dwarfs locked in a mutual orbit. As they circle each other over trillions of years, they lose energy by emitting gravitational waves, ripples in space-time itself. This loss of energy causes their orbits to slowly decay, drawing them ever closer in a spiral that ends in a cataclysm. If their combined mass crosses a critical threshold, their merger can trigger a titanic thermonuclear explosion, a Type 1, a supernova that for a few weeks will outshine the entire rest of the galaxy. These explosions are the last great fireworks the universe will ever see, briefly illuminating a cosmos that is growing steadily colder and darker with each passing trillion years. This degenerate era is a long, quiet prelude, a deep and chilling exhale before the final descent into absolute black. Is the very substance of our being, the atoms that form our bodies and our world, truly built to last forever? This question strikes at the heart of cosmic permanence. We think of a diamond as eternal, or a white dwarf star as an indestructible cinder. But what if the fundamental building blocks of all matter carry a hidden expiration date? This leads us to one of the most profound and unsettling ideas in theoretical physics, the concept of proton decay. Our current understanding of particle physics is encapsulated in the Standard Model, a remarkably successful theory that describes the fundamental forces and particles. Yet, this model is incomplete. It treats the four fundamental forces as distinct, but physicists have long sought a single, elegant framework that unifies three of them: the strong nuclear force that holds atomic nuclei together, the weak nuclear force responsible for radioactive decay, and the electromagnetic force. These hypothetical frameworks are called Grand Unified Theories, or GUTS. Many of these theories predict a startling consequence: that the proton, the stable, positively charged particle at the heart of every atom, is not truly stable at all. It could, over an almost incomprehensible span of time, spontaneously fall apart. According to these models, a proton would not simply vanish. It would decay, transforming into lighter particles, typically a positron, which is the antimatter counterpart of an electron, and neutral particles of light called photons. This process would not be quick. The theoretical half-life for a proton, the time it takes for half of a large collection of protons to decay, is staggering, around 10 to the 34 years. To grasp that number, compare it to the current age of the universe, a mere 13.8 billion years, which is only 10 to the 10 years. The proposed lifespan of a proton is a trillion times longer than the universe has even existed. The implications of this slow decay are monumental for our lonely supergalaxy in the far future. Every complex structure we know is made of atoms, and atoms are built around protons. If protons decay, then no piece of matter is truly permanent. The cold, dark white dwarfs and neutron stars that dominate the Degenerate Era would not simply cool quietly. They would slowly evaporate. A white dwarf over these immense eons would not just be a cold, dark sphere. It would be a fading cloud of disintegrating matter, its very protons turning into a faint, steady glow of light and other particles. Any remaining planets, asteroids, or cosmic dust would similarly dissolve, their atomic nuclei crumbling away. The stellar graveyard would not be a permanent resting place, but a scene of the slowest, most gradual demolition imaginable. But is this theoretical fate our actual destiny? The answer remains one of the great mysteries of science. For decades, physicists have been searching for direct evidence of proton decay. They use incredibly sensitive detectors, often placed deep underground in abandoned mines or beneath mountains, to shield them from the constant rain of cosmic rays that could mimic a decay signal. These experiments, like the Super Kamiok and detector in Japan, involve enormous tanks of ultra-pure water, surrounded by thousands of light sensors waiting to catch the unique flash of light that would be produced by a single decaying proton. So far, not a single confirmed proton decay has been observed. These null results are not failures, they are crucial data. They tell us that if protons do decay, their half-life must be longer than the current experimental limits, which are now beyond 10 to the 34 years. The search continues, pushing the boundaries of our patience and technology. If proton decay is real, it means that even the most stable structures in the cosmos, the very bedrock of reality, are temporary. It would be the ultimate erasure of the universe's material history, leaving behind only a dilute sea of light and subatomic particles. This forces a final, haunting question. If all matter and structure eventually fades, what possible form could the universe's final legacy take? Even the slow decay of matter cannot touch the ultimate structures in the cosmos. Black holes forged from pure gravity are the final monuments. They are not made of atoms or protons. They are regions where space and time have curved in upon themselves so severely that nothing, not even light, can escape their grip. Long after the last white dwarf has faded and the last proton has dissolved, these gravitational tombs will persist, becoming the most prominent and active objects in a universe that is otherwise fading into darkness. The black holes of this distant era will come in a range of sizes, each a relic of a different cosmic event. Scattered throughout the galaxy will be stellar mass black holes, the remains of massive stars that ended their lives in supernova explosions. Then there are the intermediate mass black holes, likely formed from the mergers of many smaller black holes within dense star clusters. And reigning supreme at the very center of our supergalaxy will be the supermassive black hole, a behemoth containing the mass of billions of suns, a silent monarch from a bygone age of brilliant quasars and active galactic nuclei. Their dominance is assured by their incredible longevity. Unlike stars that burn out in billions of years or protons that may decay in 10 to the 34 years, a typical black hole born from a star will last for an almost unimaginable 10 to the 67 years. This vast time span comes from a subtle quantum process predicted by Stephen Hawking. Just outside a black hole's event horizon, the point of no return, pairs of virtual particles are constantly flickering in and out of existence. Normally, these particle-antiparticle pairs annihilate each other almost instantly. But if one particle falls into the black hole while the other escapes, the escaped particle becomes real, stealing a tiny amount of the black hole's mass energy. This is Hawking radiation. It is not a fiery explosion from within, but a faint quantum mechanical leak from the very boundary of the black hole. The smaller the black hole, the stronger the gravitational gradient at its horizon, and the more intense this radiation process becomes. A small black hole radiates more powerfully and evaporates more quickly. A massive black hole with its gentle curvature has a much fainter glow and a correspondingly longer life. This means the stellar mass black holes will be the first to vanish in a final, tiny flash of energy. The supermassive black hole at the galaxy's heart, however, will outlast them all, a final island of structure in a sea of expanding nothingness. For eons upon eons, these black holes will be the last sources of power in the cosmos. The feeble energy of their Hawking radiation, a whisper of heat in a universe approaching absolute zero, will be the only game in town. The final evaporation of the last supermassive black hole will mark the true end of an era, closing the book on all large-scale structure and heralding the universe's final, featureless state. After the last black hole evaporates in a final, silent flash, the cosmos enters its longest and most silent chapter. The Dark Era is a state of near-nothingness, a universe so ancient and expanded that its very nature has been transformed. The temperature of the entire cosmos will have plummeted to a fraction of a degree above absolute zero, the coldest temperature possible. What remains is not a complete void, but an unimaginably thin and cold soup of fundamental particles and energy. This sea is composed of photons, the particles of light, stretched to wavelengths larger than the observable universe, carrying almost no energy. It is filled with neutrinos, ghostly particles that barely interact with anything, and a sparse sprinkling of electrons and their antimatter counterparts, positrons. These particles are so far apart that they might as well be in different universes, drifting for eons without a single interaction. This is the universe in a state of maximum entropy, a condition physicists call heat death. Do not picture a dramatic explosion or a freezing ice age. Instead, imagine a cup of coffee that has cooled to room temperature. The heat has not vanished, it has simply spread out evenly, achieving a perfect and unchanging balance. The entire cosmos becomes that room temperature coffee, a state of thermodynamic equilibrium where every point is identical to every other point. There are no hot spots or cold spots, no mountains or valleys of energy. This perfect uniformity is the end of possibility. With no energy differences, no gradients, there can be no engines, no processes, and no work can be done. A universe with maximum entropy has exhausted all its potential for change. It is a static, homogeneous, and isotropic void, meaning it looks the same in every direction and at every point. In such a cosmos, what is time? Time requires a sequence of events, a before and an after marked by change. But here, in the endless dark era, nothing happens. A single second is indistinguishable from a trillion years. The universe has not only run out of fuel, it has run out of events, rendering time itself a meaningless concept. This is the hypothesized final equilibrium under our current understanding of physics, the ultimate fate of a universe dominated by dark energy. Yet, even as we contemplate this absolute end, we are drawn to a final, profound question. Can anything truly be eternal, even this perfect, featureless void? Our best models point towards a cold, dark end, but cosmology is a science built on astonishing surprises. The heat death is not the only future on the table. Other, more dramatic fates are possible, all hinging on the mysterious nature of dark energy. What if its strength is not constant but grows over time? This leads to a scenario far more violent than a slow fading, an event cosmologists call the Big Rip. In this future, the repulsive force of dark energy intensifies without limit. Billions of years from now, long before stars have all died out, this force would overcome the gravity holding our supergalaxy together. The island universe itself would be torn apart. First, galaxies would be shredded, then solar systems ripped from their orbits. In the final, terrifying moments, the force would exceed the very bonds holding atoms together. Planets, stars, and every physical structure would be violently dissociated into a diffuse cloud of fundamental particles, a fate that would preclude the long, quiet Degenerate Era entirely. This is not a gentle fading, but a cosmic demolition. Yet another possibility reverses the entire narrative. What if the expansion does not continue forever? This is the concept of the Big Crunch. In this cyclical model, the combined gravity of all the matter in the universe, including dark matter, eventually halts and reverses the expansion. The universe would begin to contract, slowly at first, then with increasing speed. Galaxies would rush together, their light blue shifting into a brilliant, deadly glow. The background temperature of the cosmos would rise, eventually boiling away planets and stars. The entire universe would collapse back into an ultra-hot, ultra-dense singularity, a mirror image of the Big Bang. This singularity could then become the seed for a new universe, bursting forth in another Big Bang, giving rise to an entirely new cosmos with potentially different physical laws. This leads to the idea of a big bounce, a universe of endless cycles, where each contraction and rebirth follows the last in an infinite loop. Our entire cosmic history, from the first star to the last black hole, could be just one chapter in an endless book. Perhaps the most unsettling alternative is vacuum decay. Think of our universe's vacuum not as true nothingness, but as a field resting in a stable, but not perfectly stable state. It is like a ball sitting in a small depression on the side of a much larger hill. This is a false vacuum. If, through a quantum fluctuation, the universe tunnels into a lower energy state, a true vacuum, it would create a bubble of a new reality. This bubble would expand at the speed of light, its wall rewriting the laws of physics as it moves. Fundamental constants like the speed of light or the strength of gravity could change instantly. Atoms would cease to hold together, and the structure of matter would simply dissolve. This would not be an end born of astronomy, but of fundamental physics itself, a sudden and total transformation of reality. These speculative futures remind us that the ultimate fate of the cosmos is still an open question. Our understanding of dark energy and the vacuum is provisional, leaving room for profound discoveries. This uncertainty forces a deeply human question. If the universe can end in fire, ice, or rebirth, what role could intelligence possibly play across these epic timescales? A profound silence settles over the cosmos, and with it comes a deeply philosophical question. If a galaxy recedes beyond the cosmological horizon, vanishing from all possible observation, does it still exist in any meaningful sense? The very nature of reality becomes entangled with the act of witnessing. In our current, vibrant universe, we are privileged observers, able to trace the history of creation back to its fiery beginning. But what of the observers who might arise in the distant future, trillions of years from now, within the confines of our isolated supergalaxy? Their experience of the cosmos would be fundamentally and tragically different from our own. Their entire observable universe would be this single island galaxy. The night sky, which for us is a tapestry of countless suns and swirling nebulae, would be for them a relatively static and unchanging sphere of ancient red stars. There would be no grand evidence of a dynamic, expanding universe. The most crucial pillar of our modern cosmology, the cosmic microwave background radiation, would have faded into nothingness. That faint afterglow of the Big Bang, which we can detect with our telescopes, would have been stretched by the relentless expansion of space over trillions of years. Its wavelengths would become so long, its photons so feeble that they would carry no detectable energy, dissolving completely into the background. For these future scientists, the universe would not appear to have had a beginning. It would seem eternal, static, and alone. They would have no reason to propose a Big Bang or an expanding cosmos. Their cosmological models would likely be based on a steady-state universe, one that had simply always existed in its current island form. This is a state of cosmic forgetfulness, where the entire history of the universe, its birth in fire and its era of brilliant connectivity, becomes irretrievably lost to time. Could such a civilization ever deduce the truth? Perhaps only through the most advanced theoretical physics, by uncovering clues in the fundamental laws themselves. They might calculate that proton decay or the nature of the vacuum suggests an ultimate timeline, a finite age for matter. But without the observational evidence we take for granted, their task would be monumentally harder than our own. This startling perspective reveals a profound truth. The knowledge we possess today about the cosmos is not a permanent inheritance. It is a fleeting glimpse, a precious piece of data available only during this brief, bright window in cosmic history. Our moment to understand the universe's grand story is now, before the final pages are torn away by the expanding void. A cosmic library is slowly burning, its oldest and most precious texts turning to dust before our eyes. This is the true nature of our expanding reality, a systematic erasure of history on the grandest scale. The evidence we currently use to decode the universe's birth and evolution is not permanent. It is being carried away by the relentless stretching of space, placing a fundamental limit on knowledge itself. The first and most profound loss will be the cosmic microwave background. This faint glow is the cooled remnant of the Big Bang's fireball, the oldest light we can observe. But over trillions of years, the expansion of space will stretch its wavelengths to such an extreme that they become larger than the observable universe. The photons will be so diluted, their energy so minimal, that they will cease to be detectable at all. The universe's birth certificate will have effectively vanished. The light from the very first galaxies and quasars presents another tragedy. For many of these ancient objects, their light has already passed us by. We are seeing them now as they were in their youth, but the light they are emitting today will never reach us because the space between us is expanding faster than that new light can travel. It is a story whose final chapters we will never read. Even the crucial clues that led to our greatest discoveries are temporary. The redshift of light from distant supernova, the very data that revealed the accelerating expansion driven by dark energy, will become inaccessible. Those specific supernova will have long since exploded and faded, and the galaxies that hosted them will have redshifted into complete invisibility. Future astronomers will lack the very evidence we used to uncover the universe's dominant force. The primordial abundance of light elements, like helium and deuterium, forged in the first few minutes of the Big Bang, is another key piece of evidence. We measure these abundances in the spectra of ancient gas clouds and the oldest stars. But as the universe ages and these primordial relics evolve, die, or become impossible to observe, this direct link to nucleosynthesis will be severed. The inventory of the universe's first moments will become unreadable. This creates an information horizon, a wall beyond which knowledge is permanently lost. We are living in a uniquely privileged era, a narrow window in cosmic time when the universe is both old enough to be stable and young enough to still tell its story. We can still see the afterglow of creation and trace the evolution of galaxies across billions of years. This fleeting access to the past compels a profound responsibility. What should we do with this brief opportunity to read the universe's autobiography before the final pages fade to black? Our ability to see the cosmic dawn and the vast galactic tapestry is not a random accident of timing. It is a fundamental prerequisite for our very existence. The universe we observe possesses properties that allow for conscious life, because if it did not, we would not be here to ponder it. This line of reasoning is known as the weak Anthropic Principle. It does not claim the universe was designed for us, but simply observes that any universe capable of producing observers must, by definition, have the necessary conditions to support them. We are a product of this cosmos, and so our observational window is inherently shaped by what our existence requires. Consider a universe that was significantly older. If we lived trillions of years in the future, our supergalaxy would be the only thing visible in a black, empty sky. The cosmic microwave background would have faded into complete undetectability, and all evidence of an expanding universe or a Big Bang would be irretrievably lost. A civilization emerging in that era would have no reason to believe the universe had a beginning or that other galaxies ever existed. Their cosmology would be built on a fundamentally incomplete and isolated picture of reality. The development of science as we know it, which relies on observing a dynamic and historically rich cosmos, would be impossible. Now, consider the opposite. If we existed when the universe was much younger, only a few million years old, the necessary ingredients for life would be absent. The first stars would have just begun to form, fusing primordial hydrogen and helium into the first traces of heavier elements. There would not have been enough time for multiple generations of stars to live and die, scattering space with the carbon, oxygen, nitrogen, and iron that form planets and living organisms. The universe would be too primitive, lacking the complex chemistry that life as we understand it requires. Our present moment is a cosmic sweet spot. We exist in a brief, shining interval where the universe is both old enough to have manufactured the elements of life and young enough to still hold the evidence of its own creation. We can look out and see the afterglow of the Big Bang, and we can look around and see a universe still teeming with galaxies. This is our Goldilocks era for cosmic observation. The Anthropic Principle does not tell us why the physical constants and initial conditions of the universe are what they are. It does not solve the mystery of why dark energy has the specific strength it does. But it offers a powerful explanation for why we find ourselves situated in this particular slice of cosmic time, able to ask these profound questions. This realization places a profound and urgent responsibility upon our shoulders. We are the temporary guardians of a cosmic story that is slowly fading from view. Our civilization, arising in this fleeting window, has been given a unique chance to read the universe's autobiography before the final chapters are lost to the expanding dark. The knowledge we gather now might one day become the only remaining evidence that the cosmos was ever anything more than a single, lonely island of stars in an endless, silent night. Does our fleeting moment of cosmic awareness come with a responsibility to the future? This is not merely a philosophical exercise, but an ethical imperative that stretches across the eons. The concept of long-termism asks us to consider the potential for vast numbers of people or other forms of intelligent life that could exist in the distant future. Their well-being matters, and our actions today can shape their world in profound ways. Within our local supergalaxy, trillions of years from now, new civilizations could rise from the ashes of long-dead stars. They will be born into a universe of profound isolation, with no evidence of a cosmic beginning or other island universes. Their reality will be a solitary, seemingly eternal galaxy, and they may never guess at the glorious, interconnected cosmos that once was. We are in a unique position to prevent this cosmic forgetfulness. We could become the ancient cartographers for these future beings, creating a legacy of knowledge designed to survive the ages. Imagine launching indestructible records, perhaps made of etched platinum or advanced crystalline materials, into stable orbits around long-lived red dwarf stars. These cosmic time capsules would not carry just greetings, but the foundational truths of our cosmology. They would contain star maps showing the local group's structure before the Great Merger, the measured redshift of galaxies now vanished, and the equations describing the Big Bang and the accelerating expansion. This would be our most profound gift across time, a message in a bottle assuring a future civilization that they are not alone in history, even if they are alone in space. But what if our role could be even greater than that of librarians? The emerging field of astroengineering, or cosmic engineering, speculates that a sufficiently advanced civilization might not just preserve knowledge, but actively manage its celestial environment. This shifts our narrative from passive observers to potential stewards of the cosmos. Could our descendants learn to rekindle dying stars or shepherd comets to deliver water to barren worlds? Might they find ways to counter the local effects of dark energy or even influence the ultimate fate of the universe itself? While this sounds like the stuff of science fiction, the underlying principle is sound. Intelligence could become a force of cosmic evolution, working on timescales of billions of years to maintain pockets of light and life in an increasingly dark and hostile universe. The very fact that we can contemplate such a future, that the laws of physics might allow for it, forces us to look back at the fundamental rules of reality that make our existence and our potential possible in the first place. The arrow of time feels absolute to us, a one-way street from a definite beginning to an inevitable end. But our perception may be a local illusion, a story told within the confines of our own cosmic bubble. To grasp a far grander reality, we must turn to the theory of eternal inflation. Picture our entire observable universe with all its hundreds of billions of galaxies, not as the whole of creation, but as a single soap bubble adrift in a frothing, infinite sea. This sea is the meta-universe, a realm of hyper-fast, eternal expansion where the very fabric of spacetime is continuously giving birth to new bubbles. Each of these bubbles is a universe in its own right, nucleating with a random set of physical laws and constants. In this endless cosmic foam, the death of one bubble is meaningless. While our own universe may be destined for a cold, dark heat death, an infinite number of other universes are being born at every moment. Some might collapse instantly, while others could be filled with physics that make life impossible. Our existence here, in a universe with stable atoms and long-lived stars, is simply a reflection of our necessary presence in a bubble that allows for it. This multiverse hypothesis completely reframes the idea of an end. There is no final curtain for reality itself, only local conclusions. This perspective finds a strange echo in Einstein's theory of special relativity and its block universe model. In this view, the flow of time is a human construct. The past, present, and future all exist simultaneously in a static, four-dimensional block of spacetime. Your birth, your life, and the heat-death of the universe are all equally real, fixed locations in this cosmic loaf. From this God's eye view, the end of our universe is not an event that happens, it is simply a place. It is the final page of a book where all the pages exist at once. This challenges the deepest philosophical debates about time itself. Is time finite with a true beginning and a definitive end, a view known as temporal finitism, or is it infinite, stretching without start or conclusion, as infinitism suggests? If the universe is truly infinite in spatial extent, then even as our local region grows dark and empty, an infinite number of other galaxies and events will always be occurring beyond our cosmological horizon. The cosmic light show never truly stops, it just moves out of our neighborhood. This vast, multiversal perspective can be both a comfort and a profound disorientation. It suggests that our lonely, fading supergalaxy is not the entire story, that endings are relative to the observer. The grand narrative of a universe born in fire and dying in ice might just be the local history of our particular bubble, one chapter in an infinite, eternal library of realities. The silent, near-perfect vacuum of the dark era is not truly empty. It is a seething, frothing sea of potential, governed by the bizarre rules of quantum mechanics. In our current universe, these tiny, random fluctuations are drowned out by the grand motions of planets and stars. But in a cosmos stretched thin and cold, where no large-scale events occur, these quantum whispers become the loudest phenomena in existence. The vacuum of space itself possesses a baseline energy, and within that energy, pairs of virtual particles constantly pop into and out of existence, borrowing energy from the void for an impossibly brief moment. This is the quantum foam, the fundamental texture of reality, and in an eternal, nearly static universe, it holds the potential for the most dramatic rebirths. Physicist Edward Tryon once proposed a stunning idea that our entire universe could be the result of a quantum fluctuation from nothing. In the far future, the reverse could also be true. Through a process called quantum tunneling, a new universe could spontaneously nucleate from the vacuum of our old, dying one. A tiny bubble of a new space-time, with its own random set of physical laws, could appear and begin inflating at a fantastic rate, creating an entirely new cosmic story entirely separate from our own. It would be a universe born in the graveyard of another. This leads to one of the most unsettling thought experiments in all of physics, the concept of Boltzmann brains. Named for the physicist Ludwig Boltzmann, it stems from a statistical view of reality. In a universe that exists for an infinite or near infinite amount of time, every possible arrangement of particles, no matter how improbable, will eventually occur by random chance. This includes the spontaneous, random assembly of a fully formed, self-aware brain, complete with false memories of a past that never happened, floating alone in the void. The probability of such an event is astronomically low, so low it is virtually zero on any human timescale. But over trillions upon trillions of years, the improbable becomes the inevitable. This creates a profound philosophical paradox. Which is more statistically likely, the long-ordered 13.8 billion-year chain of events from the Big Bang to the evolution of our civilization, or the random, momentary fluctuation that creates a single, disembodied consciousness with the illusion of that history? Our entire experienced reality could, in principle, be the fleeting delusion of such a Boltzmann brain. While most scientists consider this a logical curiosity rather than a serious description of our world, its very possibility forces us to confront the nature of consciousness and reality in an eternal cosmos. The quantum realm assures us that the story does not have to end with a simple, linear fade to black. Even in the deepest, darkest silence, the potential for something new, something strange, and something conscious always remains, flickering in the infinite night. The cosmos does not offer us a purpose, but it provides the raw material from which we can forge our own. Physicist Steven Weinberg once remarked that the more the universe seems comprehensible, the more it also seems pointless. He was observing that the fundamental laws of physics contain no commandment for how we should live, no inherent valuation of a symphony over silence. Yet this very pointlessness is the canvas upon which our meaning is painted. If the universe were stamped with a single, obvious purpose, our own choices and loves would be mere footnotes to a predetermined script. Their value would be borrowed, not earned. The transience of everything from a star to a civilization does not drain our moments of significance, it concentrates it. A song is not beautiful because it lasts forever. Its beauty is woven into its fleeting notes, the very fact that it exists for a short time and then is gone, leaving an echo in the memory. Our lives are like that song. The love between two people, the struggle for justice, the creation of a work of art, the thrill of a scientific insight. These are not cosmic events on the scale of supernova. But they are real and they matter to us. They matter because we are the part of the universe that has awakened and can feel, think, and care. We are the universe's mechanism for generating meaning. The ultimate philosophical rebellion against a cold, expanding void is not to despair, but to declare that our experiences are the very point. Our brief window of consciousness is a flickering light in an immense darkness, and that is precisely what makes it radiant. The knowledge that the stars will one day fade does not invalidate the wonder we feel when we look up at them tonight. It deepens it. This search for meaning, this insistence on finding purpose in the face of an indifferent cosmos, is perhaps our most profound human achievement. It prepares us to take all these cosmic truths and ask the final, most personal question of all. Our universe began in a state of impossible order. From an initial condition of extraordinarily low entropy, a hot, dense fireball erupted in the Big Bang, setting into motion a one-way journey toward disorder that continues to this day. In those first fleeting moments, energy coalesced into the fundamental particles that would become the building blocks of everything. As the cosmos expanded and cooled, these particles settled into hydrogen and helium atoms, which later gathered into vast clouds under the pull of gravity. Within these cosmic nurseries, the first stars ignited, their nuclear furnaces forging the heavier elements that would one day form planets and life. This was the dawn of structure, a period of intense activity that gave rise to the brilliant galaxies we see today. We are living in the golden age of this process, the Stelliferous Era, a time defined by light and ongoing creation. Yet this very structure contains the seeds of its own dissolution. The formation of stars and planets represents a local increase in order, but it is paid for with a far greater cosmic debt of disorder, primarily through the waste heat radiated out into the universe. Every star that shines increases the total entropy of the cosmos, a debt that must eventually come due. The engine driving this grand narrative is the relentless increase of entropy, a measure of the universe's disorder. The initial state of the Big Bang was one of remarkable, unexplained uniformity and low entropy, a tightly wound spring that has been uncoiling for nearly 14 billion years. As this spring unwinds, it powers every process we hold dear, from the fusion in stellar cores to the biological processes of life itself. We are all temporary eddies in this vast, one-way river flowing from order to disorder. This journey leads us to our current epoch, a fleeting window where galaxies are still visible and stars still burn, but the river's flow is inexorable. The ongoing acceleration of the universe's expansion, driven by dark energy, ensures that the future will be one of increasing isolation and stillness. The great galactic cities will drift apart, their lights fading as the space between them stretches into an unbridgeable gulf. Our own local group of galaxies will consolidate into a single, aging supergalaxy, a final island in the void. Within this last bastion, the era of star formation will inevitably end as the last reserves of interstellar gas are consumed or expelled. The universe will then enter the Degenerate Era, a twilight epoch dominated by the cooling corpses of stars. White dwarfs and neutron stars will slowly radiate their remaining heat away into the ever-colder cosmos. If the hypothetical process of proton decay is real, then even these stable-seeming remnants will not last. Over timescales that dwarf all of previous cosmic history, the very protons at the heart of every atom will disintegrate, dissolving all solid matter into a thin haze of light and subatomic particles. The final monuments, the black holes, will themselves succumb over even longer periods. Through the faint quantum process of Hawking radiation, they will leak their mass away, eventually vanishing in a final, silent puff of energy. This leads to the ultimate state, the dark era and the heat death of the universe. The cosmos will become a vast, cold, and nearly perfect vacuum. With no energy differences, no hot or cold spots, no further work can be done. The universe will have reached a state of maximum entropy, a final, uniform equilibrium where time, as a marker of change, loses all meaning. This grand synthesis from a hot, dense beginning to a cold, empty end is the overarching story told by the laws of physics. It is a story of transformation on the grandest scale, where every galaxy, star, and living creature is a temporary configuration in the universe's slow, majestic march toward equilibrium. Understanding this complete arc forces a profound question about the nature of reality itself. Why did our universe begin in such a special, low-entropy state? And what does that unique starting point tell us about the fundamental laws that govern everything from the quantum realm to the cosmic horizon? Our cosmic forecast is built upon the bedrock of known physics, but that bedrock has cracks we cannot ignore. Predicting the far future requires a degree of humility, an acknowledgement that we are extrapolating from a map that is still missing entire continents. The grand timeline from the Stelliferous Era to the Dark Era is our best guess, a compelling story woven from the threads of general relativity and particle physics. Yet, several profound unknowns could unravel this entire narrative. The first and most significant mystery is the true nature of dark energy. Our current models treat it as a cosmological constant, an unchanging force inherent to the vacuum of space. But what if it is not constant at all? What if this repulsive energy evolves, growing stronger or weaker over time? A strengthening dark energy could lead to the terrifying Big Rip, shredding our supergalaxy eons ahead of schedule. A weakening one could, against all odds, allow gravity to reassert its dominance, opening the door to a cyclical universe. We simply do not know which, if any, of these paths is real. Then there is the enigma of proton decay. Is the proton, the very foundation of atomic matter, truly stable, or does it carry a hidden half-life of 10 to the 34 years? The answer determines whether the stellar corpses of the Degenerate Era will endure as permanent monuments or slowly evaporate into nothingness. Our most sensitive experiments have yet to witness a single proton decaying, pushing the possible timeline for this process into realms so distant they challenge the very concept of time. Beyond these known puzzles lies the quest for a final theory, a seamless union of gravity and quantum mechanics. We lack the rules to describe the universe's first instant, and by extension, its very last. What happens when a black hole evaporates completely? What is the true nature of the vacuum from which a new universe might quantum tunnel? Our current physics hits a wall at these extremes. Perhaps the most exciting possibility is that of the unknown unknown. The history of science is a graveyard of settled certainties. We once believed the Milky Way was the entire universe, that the cosmos was static and eternal. Each revolution came from discovering something we did not even know to look for. Dark matter and dark energy themselves were once unimaginable. What other forces, particles, or principles remain hidden, waiting to be discovered in the vast darkness? A future civilization might uncover a form of energy or a law of physics that completely rewrites the final chapters, offering possibilities we cannot yet dream of. This uncertainty is not a failure of science, it is its very heart. The fact that the universe's ultimate fate remains an open question is a thrilling invitation. It is a call to keep looking, to keep questioning, and to remain open to the wondrous surprise that the cosmos has always, and may always, hold in store. A century ago, our cosmic perspective shattered. We believed the Milky Way was the entire universe, a lone island of stars in an infinite, static void. Then, at the Mount Wilson Observatory, Edwin Hubble peered through the most powerful telescope of his era and saw something that would change everything. He was studying fuzzy patches of light, then known as spiral nebulae. Astronomers debated whether these were small, nearby clouds of gas within our own galaxy or vast, distant collections of stars in their own right. Hubble found his answer by identifying a special kind of star within the Andromeda Nebula, a Cepheids variable. These stars pulse with a regular rhythm, and their pulse rate is directly tied to their true brightness. By measuring how bright the star appeared from Earth and comparing it to its known true brightness, Hubble could calculate its distance with remarkable precision. His result was staggering. Andromeda was millions of light-years away, far beyond the borders of the Milky Way. It was not a nebula at all, but an entire galaxy. The universe, in an instant, became 1,000 times larger. This revelation was only the beginning. Hubble, building on earlier work by astronomer Vesto Slipher, began measuring the light from these newly discovered galaxies. Slipher had found that the light from most of these spirals was shifted toward the red end of the spectrum. Hubble connected this redshift to distance. He discovered a direct and simple relationship. The farther away a galaxy was, the faster it appeared to be receding from us. This was the birth of Hubble's law, the first direct evidence that we live in an expanding universe. Space itself was stretching, carrying the galaxies along with it. The entire cosmos was in motion, flying apart from a primordial beginning. This story of discovery is not complete without a theoretical genius working in the background. 2 years before Hubble published his definitive data, a Belgian priest and physicist named Georges Lemaitre had already solved Einstein's equations of general relativity and derived a model of an expanding universe. He proposed that the universe began in a hot, dense state, a primeval atom that exploded outwards. Lemaitre had theoretically predicted the very expansion that Hubble would later observe. For decades, his pivotal role was overlooked, his groundbreaking paper forgotten by many, but history now rightly credits him as a father of the Big Bang theory. This journey, from Slipher's first redshift measurements to Lemaitre's equations and Hubble's confirming observations, forms the bedrock of modern cosmology. It is a powerful reminder that our knowledge of the cosmos's fate, from its fiery birth to its cold, dark end, was not handed to us. It was painstakingly built, observation by observation, insight by insight, by individuals who dared to look deeper and question everything. Their legacy is our understanding that we live not in a permanent, static realm, but in a dynamic and evolving cosmos with a story that is still being told. Astronomers of the distant future will face a sky in constant, dramatic flux. The serene band of the Milky Way will begin to churn and distort as the colossal Andromeda galaxy looms ever larger, its spiral arms tearing apart under the immense gravitational pull of their mutual dance. This merger will be the most spectacular celestial event ever witnessed, but for those trying to map the heavens, it will be a period of profound disruption. The familiar constellations will be erased, replaced by a brilliant, chaotic swarm of new stars and glowing nebulae. Amid this local chaos, a far more insidious loss will be underway. The faint, redshifted light from galaxies beyond our local group will be stretching into near invisibility. The telescopes we use today, even our most powerful space observatories, would be rendered nearly blind in this future era. The race to decode the cosmos will demand a radical reinvention of astronomy itself. Future scientists will need to abandon traditional optics and learn to see the universe in new ways. They will turn to gravitational wave observatories, listening for the ripples in spacetime from colliding black holes and neutron stars. These signals, unaffected by the dimming of light, will become a primary tool for understanding the large-scale structure of the cosmos. They might also build vast arrays to detect the ghostly passage of neutrinos, particles that travel almost unimpeded across the universe, carrying information from its most violent and hidden corners. To catch the last whispers of optical light from receding galaxies, they will likely construct telescopes of unimaginable scale. Imagine observatories built on the far side of the moon, a location permanently shielded from the radio noise of Earth and offering a stable, airless platform for colossal mirrors. Or perhaps they will assemble intricate interferometers in the calm of deep space, linking instruments across millions of miles to achieve a resolution far beyond anything possible today. This is not merely a technological upgrade, it is a desperate salvage operation. Every observation will be an act of rescuing data from an event horizon of expanding space, a frantic effort to capture the universe's story before the final pages are torn away. This relentless pursuit against an inexorably darkening sky will stand as the ultimate testament to an insatiable curiosity, a drive to understand our home even as its walls close in and the windows to the outside world are sealed shut forever. Our long journey through cosmic time brings us to a final, humbling perspective. We have traced the arc of the universe from its vibrant, star-filled youth to its eventual cold and silent old age, a transformation driven by the relentless expansion of space and the steady increase of entropy. This grand narrative is not one of cyclical renewal, but of a one-way journey from a state of intense order to one of ultimate disorder. The future isolation of our galaxy and the fading of all external light frames our present era not as the norm, but as a fleeting cosmic spring, a brief and brilliant window where the universe is alive and knowable. Astronomer Martin Rees captured this perfectly when he stated that the cosmos is not required to be in perfect harmony with human ambition. The universe follows its own physical laws, indifferent to our hopes or our presence. This is not a cause for despair, but a clarion call to awareness. Our profound responsibility, our unique privilege, is to learn as much as we can, to wonder without limit, and to cherish this fleeting cosmic dawn we are so fortunate to witness. We are the universe awakening to itself, if only for a moment. I would love to hear your reflections on this vast future. What aspect of this cosmic fate intrigues or troubles you the most? If this journey through time and space expanded your mind, please subscribe for more explorations into the deepest mysteries of the universe.